3.2 Day 5 notes. We're going to connect a few dots for linear regression, hence the title, Putting It All Together. So, in terms of our wisdom, the first part, correlation and regression are powerful tools for describing the relationships between two variables, but you should be aware of their limitations. And there's three key ideas we're going to talk about. So the distinction between explanatory and response, that's the first one, that's a big one. You know, explanatory, like my X there, goes on the X-axis. So let's look at the first example here, and this is one we've done in the past with the trucks. So what's the difference between these two? Well, you should notice like the X and Y variables, they're switched. So one of them predicts the price from the miles driven. The other predicts the miles driven based on the price. Okay, so which values are the same? And you have the outputs right here. So similar values will be the R squared, right? So we know that correlation, it doesn't care what's on the x-axis, what's on the y-axis. So that's the first part. R squared and R are going to be the same. So they don't even have any units. So they have no units, and they don't make a distinction about who's on the x-axis, who's on the y-axis. They just measure the linearity. So that's really the only thing that's the same here. You kind of see the same pattern of points just flipped. Okay, so let me scroll down here. So what's different? Well, almost everything else we have up here is different. So the values for S are different, the slopes are different, the y-intercepts are different. So all those things are different here. So the slope, the y-intercept, and S are all different. If I could just scroll down again here. So those are all different. And then it says, does it matter, question 1 there, Q1, does it matter which variable is X and which is Y? Well, yeah, it does. We want the independent variable, the explanatory variable on the x-axis for 1. So yes, for the LSRL, the slope, the y-intercept, and S, those would all make a big difference. When does it not matter? Well, it's not going to matter for correlation. So that's the point. So the second key of wisdom here, correlation and regression lines describe linear relationships. So they try to measure the linearity between two things. So let's look at the 4 dot plots here. This is a really cool example. I want to give you a second. Which one do you think has the highest association? So of these 4 graphs, which one might have the highest association? And I try to draw lines through these, like what I thought the best fit line was here. So C there, it would be along these points almost perfectly, but then that influential point up there would pull the line up a little bit. And then D looks like almost straight up and down, but then obviously that influential point pulls the line over. The scales are a little bit different among these, so just note that. So whichever one you think has the highest association, this is why I wanted to illustrate this example for you. They actually all have the same exact correlation. It's my surprise face, little emoji. They all have the same exact correlation. They are all R equals 0.81. And they all follow this line, y hat equals 3 plus 0.5x. And mine may look a little different. Well, for one, I just kind of gave a little sketch there what I thought. But they're also on different scales here, so that would change the way the line looks too. But if you calculated it, they all have the exact same correlation and the exact same regression line. So this is actually a famous example. These 4 graphs, a guy by the name of Frank Anscombe came up with this. So why do I show you that? To tell you that they all have the exact same correlation. Well, that's kind of the note I want to make here. What does correlation tell you about and not tell you about? Well, it tells you nothing about the form, like linear, or nonlinear, obviously. That's what we just illustrated. So it only gives you information about the direction and strength of the relationship. Question 2. What should you always do before calculating the correlation or least squares regression line? Well, to see if a linear model is even appropriate at all, let's look at the scatter plot. That's the point I want to get across to you. So you should always plot your data, make a scatter plot. That's before doing any calculations. These calculations, yeah, they are summaries. They are values that represent. But we need to actually look at what the data looks like. So actually observe the overall trend. It's another emoji. Observe the overall trend of the scatter plot. Because correlation in itself is only a part of the story. So that's just a supplement to your analysis. It's not the whole story. So our third key here, correlation and least squares regression lines, aka LSRLs, are not resistant, which means they could be influenced by outliers. So look at this example 3. It says here's a scatter plot showing the cost in dollars and the battery life in hours for a sample of netbooks, which are small laptop computers. What effect do the 2 netbooks that cost $500 have on the equation of the least squares regression line, correlation, standard deviation of the residuals, and R squared? Okay. So this line here is actually the LSRL, as it is. But without these 2 points, it looks like there would be a linear trend this way. So these 2 $500 netbooks, that's these guys down here. What does that do to the line? Because otherwise, the line would look more like this. So this would be like the line without those 2 outliers. So we can see, just compare the lines, you can see the 2 influential points in red here from the $500 netbooks. What would happen? So without them, you have kind of this obvious correlation, this line, and then with them, what happens? So if you have those 2 netbooks in the data set, one, it definitely decreased the slope, right? So the orange line was without them, and the teal line here. So the slope is definitely decreased. In fact, it's negative now as opposed to positive. It increases the y-intercept. So the y-intercept would have been here, and now it's here. In terms of S, that's the standard deviation of the residuals. It would increase the value for S because now you have a lot more variability. Instead of this grouping, and now you include these, that's a lot more variability you have to account for. And so that would also decrease the value of R and R squared. So it weakens the correlation. And both of those are just due to the added variation. So the S and R squared result, without it, much tighter grouping. With it, a lot more variation. So that's what those are due to. Who would ever pay $500 for a netbook? I'm not really sure, especially ones with terrible battery life. There better be something really special about those. Okay, so the next piece here, outliers and influential observations in regression. So let's distinguish between what it means to be an outlier and then what it means to be actually influential, because the influential one's a little bit more specific. So in general, least squares line, that's the sum of squared errors. It makes the sum of the squared errors as small as possible. Hence the name least squares. A point that is extreme in the x direction, so right-left, like the x-axis. If it's extreme to the right or left, with no other points near it, will actually pull the line toward itself. And those are the points that we call influential. So influential points are like outliers, but they're far right or far left. They really pull the line. An outlier in general is just a point that lies outside the overall pattern. Points that are outliers in the y direction, but not in the x direction. So they're outliers like above and below the line, but they're still like in the middle of the data set. They're not far left or right. So if you're an outlier in the y direction, you can have a large residual, and other outliers may not have like such large residuals. So we say it's influential for a statistical calculation. If you removed it, that would actually like noticeably change the result of the calculation. I'm not talking about like by 0.01. I'm talking about like substantially changing it. So points that are outliers in the x direction, again that's right left, are often the influential ones. So they're more than outliers if they're to the far right or far left. Those are actually the influential ones that will pull the line. So how do outliers affect the correlation, the least squares regression line itself, and the standard deviation of the residuals? That's S. Okay, so outliers will make the correlation weaker. So it'll like detract from the linear trend. So it would definitely decrease R, the correlation. In terms of the line itself, so it will pull the LSRL and it'll change the slope in the y-intercept, particularly if it's an influential point. And in terms of S, the standard deviation of the residuals, well, it increases because there's more variability in the data. So from the last example, the 2 netbooks that cost $500, those were definitely influential because they weren't just outliers like above or below the line here in the middle. They were outliers way out here to the right. So you'll notice like what it would have done to the line is pulled it all the way down. And again, if you think back to the example where we think about these as like the middle, like the X bar, Y bar, the mean point, that's like the door hinge. And there's like springs connected to this, like the residuals. If we drew the vertical residuals, they were like springs. So this really pulls the line down. And the door hinge is in the middle. This pulls the line all the way down. All right, so scrolling down here. Are all outliers influential? And the answer is no. That's the distinction we're trying to make there. So no. Outliers vertically, like they're vertically stacked above or below the x-mean, so right in the middle on the x-axis, they have little influence on like pulling the LSRL. Outliers that are far from the x-mean to the right or left, those are the ones that pull the line and are influential. Okay, last little bit here, number 4, key to success. Don't forget, association does not imply causation. For those of you in AP Psych, that also means correlation does not imply causation. The definition here, just because something, even a strong correlation, doesn't mean like a change in X actually causes a change in Y. And let's illustrate that with the next example, the NBA example. So it shows the relationship between fouls and then the number of points for NBA players in 2010-2011. There's a lot of data points on here. So when you're asked to describe the association, and this goes back to 3.1, don't forget the acronym. That's DOFS, D-O-F-S. Direction, outliers, form, and strength. So we can actually do this in one sentence. And don't forget, we need to add context. So words from the problem when we describe this. So let's start out with, there was a strong, relatively strong, I don't think it's weak, positive. So strong and positive, that knocks out the strength and direction. Strong, positive, linear, that knocks out the form. Right now it looks linear. I honestly would need some more evidence, like the residual plot, for example, to actually say, yeah, it's linear for sure. Because maybe this thing would curve. If I got some more data, I don't know if there's any more NBA players I could look at, but maybe there's a slight curve. I can't really be sure. But for now, it looks approximately linear. So a strong, positive, linear association. But right now I would lose points because I'm lacking context. I'm not talking about what that applies to. So words from the problem. Between fouls and turnovers. For what group? For NBA players in the 2010 to 2011 season. So that covers the context bit, so that's done. In terms of outliers, maybe there's no outliers. I was thinking perhaps this player, who apparently scores not that many points for how many fouls he commits. So maybe I'll just make one note. Maybe there's a possible outlier for the player who scores about 325 points. There we go. And then I just added in what I thought the regression line might look like my best fit line. And because the Dallas Mavericks won NBA championships in 2011, I figured I'd put a little shot of Dirk Nowitzki into this one. Definitely the prettiest NBA player of all time right there. All right, so let me scroll down again here. Should NBA players commit more fouls if they want to score more points? Okay, not only does that sound ridiculous, but don't be fooled. Like, I know just because the data, like, oh, look, yeah, the more fouls, in general, the more points. That doesn't mean that this holds because, and the point we just talked about, strong correlation doesn't imply causation. So, no, more fouls does not imply more points for these players because correlation does not imply causation. And that's a pretty ridiculous claim. All right, that's all for these notes. I'm Mr. Bishop. That's Dirk Nowitzki. I'll see you in class tomorrow.